A very warm welcome to all of you to the seminar and lecture series talk this evening. This platform is created to enable an interaction between academic stalwarts and uh, with a larger audience that brings us closer to path-breaking and pioneering scholarship through our distinguished speakers. And it gives me great pleasure to introduce our speaker for today, Professor Pankaj Joshi from Ahmedabad University School of Arts and Sciences. Professor Joshi is an eminent physicist, an expert on cosmology, and he presently anchors the International Centre for Space and Cosmology at Ahmedabad University as its director. He was senior professor at the Department of Astronomy and Astrophysics at the Tata Institute for Fundamental Research, Mumbai, before joining the Charotar University of Science and Technology, the Charosat, as provost and the director for the International Centre for Cosmology, before joining Ahmedabad University, that is. His research interests are general relativity and cosmology. He has made fundamental contributions to black hole physics and gravitation theory. His extensive analysis of general relativistic gravitational collapse has been widely recognized for providing significant insights into the final fate of massive collapsing stars in the universe, the formation of space-time singularities, and cosmic censorship. He is an elected fellow of the World Academy of Sciences, Italy, the Indian National Science Academy, New Delhi, and the National Academy of Sciences, India. He has also been acclaimed by eminent scientists like Dr. APJ Abdul Kalam, Dr. R. Chidambaram, Dr. Jayant Narlikar, and several such leaders in sciences as an eminent scientist in the field. On behalf of the Seminar Lecture Series Committee, I welcome Professor Joshi to deliver his talk titled At the Heart of Our Galaxy, Shadows and the Singularity.
Okay. Thank you so much, Sarthak, for your very kind words as well as your effort. I very warmly thank the School of Arts and Science, though I am part of it, but still, their effort and all the attention that they gave to this talk, I am very grateful. There have been exciting developments recently on, you see, our observations of the cosmos, our observation of the universe. And at the center of all these developments is one particular development that is imaging now the centers of the galaxies. You see, as you know, we are ourselves part of, the Milky Way Galaxy. And recently, that is few months ago, in the last year, there was a big event capturing the image of the center of our own galaxy. Earlier, before that, they had seen the center of M87. It is a much larger galaxy than our own. I will talk about all this, but what I am trying to tell you is that this has created considerable excitement around what is called the science of black holes and the science of space-time singularities and so on. So I can also operate from the computer. Okay. Now it seems to be going. Okay. You see, typically we are all very busy with our day-to-day business and so many things to do every day, and the planning for the next day, and we are even talking about planning for the year and so on and so forth. All the same, you see, we are part of the universe, and once in a while it comes to our consciousness, what is this big universe? And it is in the child's consciousness, in the thinking of the children, that the universe mirrors a lot. All of you would remember watching the cosmos. Once upon a time, such was the situation and such was the case, medieval Europe or something like that, that here is the canopy of the stars and you should not try to look beyond that. उससे बाहर नहीं देखने का. There might be unknown forces, there might be dangerous forces, and you may be damaged. But then man's curiosity is immense, and the instruments were discovered, such as the Hubble Space Telescope and the Chandra telescope. I'll be telling more about Professor Chandrasekhar in a moment. But this X-ray telescope has been named after Professor Chandrasekhar, and the big massive collapsing stars or the centers of galaxies where very high energy phenomena is happening, there the X-ray emission is very prominent. So this is a telescope dedicated to X-ray images. And then, as I will tell you in a moment, over the world, all over the world, so much effort is being put in nowadays. In fact, SCA, that is the Square Kilometer Array, TMT, that is the 30-meter telescope, LIGO, you might have heard, the laser interferometric gravitational waves array, or related to gravitational waves in the universe, black hole collisions and such things you might have heard. LISA, they have no money for that at the moment, but I think who knows, suddenly technology may be discovered to reduce the cost, and then LISA is, you see, in the outer space that you are putting up the gravitational waves. And what I'll be talking more about is this Event Horizon Telescope, because this images of the centers of the galaxy, that is related to the Event Horizon Telescope. And then there are others. The very important point that I am trying to make is here on Earth, we are sitting, we are standing, we are conducting all our day-to-day affairs. Gravity is holding us. The force of gravity makes it all possible to do whatever we are doing. Of course, we forget most of the times that it is the gravity. But then you all have read, I am sure, in your textbooks or sci-fi or wherever, that in different planets, even on Moon, the gravity is different compared to Earth, and so on and so forth. So here, when you look at the center of the galaxy, for example, our own galaxy, then there are some 4 to 5 millions of solar masses sitting there. Now, I'll just come to it in a moment, but Sun is so big compared to Earth, and then millions of solar masses, and then that M87 I was talking about, it is even thousands of times bigger than that. So billions of solar masses, you see, put together in a small space. In a small amount of you see, a span of space, so much of mass is put together. And when you look at, for example, the skies using the Hubble telescope, this is what you kind of see. Now, there is a big story here. I would not have time to tell you, but Hubble, for the first time, from his Mount Palomar Observatory telescope, saw the objects out there, and he said, no, these are not stars, definitely. They cannot be stars, because all we see, you see, with naked eyes are stars out there. But then he said, these are not stars, these are, nebulae. I think, he gave the name nebulae. So then it turned out that each of them are, in fact, bigger galaxies. This is a close-up image, and each of the galaxies, this is one of such galaxies, actually. So each of these objects, for example, is One of them is this, you see, galaxy, and here at the center you see this big bulge. Okay, this is where a lot of mass is concentrated. This is M87, far away, out there. This is another such galaxy, you see, and we are in a kind of one arm of this galaxy, like a dot. I mean, entire solar system, all of our solar system. So you see, we do very important things here in Ahmedabad and in Gujarat and so on and so forth. But we are, just a small part. There are big stars in the cosmos. Just to give you an idea of the scale, I have given this, you have Arcturus, and then you have Pollux, Sirius, and in one corner somewhere, like P, our sun is sitting there. So what I am trying to tell you is how big, because this is going to be the main topic of my talk also, big stars and their final fate. And then when you look at the sun and our planets, you see how big was the sun? This big, as you saw. Okay, yeah, this big. This is the sun. Okay, so it is just this big. And now, even there, what you see is compared to sun, what the Earth is. So there we are, you see, in the 5 continents and in Asia, and then the Asmita of India. So all this big universe has, you see, come out as the theory tells us, the Einstein's theory of gravity, from massive blast, which is called a space-time singularity. It's called the Big Bang singularity. Actually, it has come from there, and then this is the Large Hadron Collider. We try to mimic, you see, the very high energy happenings, because as I will explain to you, the energy scales are extremely high. I mean, see, what are the highest energy scales we have seen on Earth? Bomb blast, in a short span, big energy, is released. That is a bomb. But then beyond that, the nuclear fission, you see, breaking the atomic nucleus. Beyond that, we don't have higher energies here on Earth. But if you look at the sun, or if you look at the stars, how they give out their energy. I was just telling my friend Jinal here that you see, there is a fusion of the atoms in this stars like sun. Sun is not the concrete object like our Earth and all that. It's all a big ball of hydrogen. Now hydrogen, what it does in a balloon. If you put the hydrogen, ऊपर चला जाता है ना immediately. Very difficult to hold the hydrogen. But the sun, the gravity is so powerful that the hydrogen is held together in a huge, mass, 11 lakhs times the mass of this Earth. And there, what is happening is fusion is occurring. Hydrogen atoms are fusing, creating helium. We tried to create, this kind of large hadron colliders, but I am, going to try to, argue that we need not, spend so much money on this kind of, big machines, because you see, as a cosmologist, I can try to do that. But the point is that we have natural accelerators, natural very high energy, factories, or the very high energy. I don't like to use the word factories or machines. I like to say that these objects are there where natural accelerators, natural extreme high energy objects are available in the universe. And here, now, you see, trying to focus a little bit more, As I told you just in a moment before, sun's energy comes from the fusing of hydrogen into helium, but then helium will fuse into higher elements, carbon, and so on and so forth. Finally, there will be what is called, iron. That is the end of the nuclear, fusion reaction. But then, sun starts cooling, because you can't, go further than that, and then its outer layers will spread away, and its inner part will collapse to what is called a white dwarf. This was the big work, in the early part of the 20th century, Chandrasekhar and others. I'll just mention that in a moment, but the point is that sun does it very slowly, just for us, It has lived, 500 crores of years, and is still going to live another 5 billion, more years. So we have enough time, to do everything. All of you can make your careers, jobs, and families and whatnot. But for massive stars, it is not like that. I showed you the pictures, right? That many stars are very massive, much more massive than the sun. So they are as massive as 10, 20, 30 solar masses, for example. So those stars burn much faster. But before that, I'll tell you, a quote from the original, paper of Chandrasekhar. He said, I told you, star of small mass must be essentially different from the life history of a star of large mass. That is what I told you just now. But the important point is that a star of large mass, a star of large mass cannot pass into the white dwarf stage, and one is left speculating on other possibilities. This is, the origin of entire black hole physics, really. What will happen to very massive stars? As I told you, the massive stars burn much faster. They are much more luminous, and they just live few millions of years. And then what happens? For sun, we know, as I told you, it stabilizes to a white dwarf. But for much more massive stars, what will happen? That is rather unknown. And even today, that is one of the most important frontier topics. Now, what is needed here is the general theory of relativity. Here on Earth, we can, get away using the Newtonian gravity. But when you talk of very high gravitational fields, like the, stars much more massive than sun and so on, then in that case, you have to use the general theory of relativity. This is, of course, the special relativity equation, but his gravitation theory basically makes a beautiful use of what is called the geometry of space and time. We had a very nice course in the last semester with many of our students here. What is general theory of relativity, and so on and so forth. But basically, it deals with what is the geometry of when you put space and time together. Newtonian mechanics, or what Newton had done, was space was completely separate. Time is completely separate. He said time flows like an ever-going river, and whatever that kind of a description was given for time, completely independent, completely separate. And then similarly for space also, he had completely different description, and that is what the classical mechanics of Newton is. But in Einstein theory, you put the two things together. I would not go into the details of that, but I can only tell you that Einstein gravity has created nowadays fantastic concepts as well as impactful observations, both. Earlier, it was not the case. When Einstein gave his theory, for 20, 30 years, it was very quiet. I am just coming to that. But in the recent years, you see, we have black holes, we have Big Bang, we have gravitational waves, a big news, and then multiverses like our own universe. Are there other universes out there? And time warps, time travel. Can you go back into the past? So this is all being seriously debated. I mean, using mathematics as well as, you see, the concepts of theoretical physics, which was only a total fiction once upon a time. Space-time singularities, and the big question whether they are visible or not, the naked singularities. So the first, work on gravitational collapse, because as I told you, when you want to measure the life history of a massive star, you have to use general theory of relativity. Oppenheimer and Schneider, and in India, in a similar work, that in Calcutta, they did works outlining what will happen when a massive star collapses, when a massive star shrinks. And then it was in this works that the concept of black hole was born. What happened was the entire star was collapsing in the Oppenheimer, Schneider, and Dutt model. And then what was created was, later on these names were given: event horizon and trapped surfaces and black holes. These names were not given at that time, but the concept and the whole theory was worked out. But in 1939 itself, Einstein himself was very unhappy with this work, and he says, nothing doing. A star cannot collapse like this. It cannot shrink like this. There must be some stability somewhere. Einstein wrote a paper, and then everything was quiet, of course. I mean, when Einstein writes and saying, oh, no, this will not work. So then, people start thinking naturally. Of course, Einstein did make many mistakes, but he only, said very late that I made a mistake. So till that time, you see, everyone was sort of thinking very hard, or stopped thinking completely. कि भाई आइंस्टाइन ने बोल दिया है, तो आज भी ऐसा होता है. Human sort of psychology is similar most of the times. But here, you see, from this concept, from this work, this idea of black hole came up. Oppenheimer and Schneider work, and that work. So I should say a few words here. This is kind of an object which is the final outcome of the gravitational collapse of a star. Now, what is gravitational collapse of a star? When, as I just told you before a moment, all the internal fuel is existed within the star, then it's like a balloon. If you release the air from the balloon, then you see the rubber shrinks. So a star is also balanced between the gravity, which is pushing in, and this nuclear processes that I was mentioning, which are happening inside, which push out. Now, once the nuclear processes subside within a massive star, because the fuel is over, then the gravity compresses the star, and outcome of that process is this kind of an object which was worked out by Oppenheimer and Schneider. But as I said, nobody looked at this work. But then in 1960s, something very interesting happened. Martin Ryle and some other radio astronomers looked far away in the skies, and they observed what are called radio galaxies. Radio galaxies are the objects which give out huge amount of energy. अब इतनी एनर्जी कहाँ से आएगी? From where will you get this energy budget? Nothing can explain. You see, nuclear fission, fusion, वो सब, nothing of that kind is going to work. So, the concept of, you see, the Oppenheimer-Schneider, that was recalled. कि हाँ, ये Oppenheimer-Schneider had worked out this kind of, gravitational collapse of star, and maybe it's the gravity only that can help us. The four fundamental forces, as you know. You see, the strong and the weak and the electromagnetic forces and gravity. So none of the three forces can help you create this much of energies. So it is the gravity, and the workings of the gravity that can only help. And then this was recalled, but Oppenheimer-Schneider work had a lot of limitations in the sense that they took a very small, simple model with a lot of assumptions. But then an assumption was made कि चलो जो Oppenheimer-Schneider model में हुआ था, just like that, all the stars will collapse into black holes, and then people started working out a lot of physics of black holes. John Wheeler, Roger Penrose, Stephen Hawking, Kip Thorne, and the classical and quantum aspects of black holes were worked out, thermodynamic analogies. Basically, a black hole has what is called a space-time singularity at the center. Now, this is a new word that I am introducing. The entire star, that collapsed, that shrinks into what is called a singularity. A star which lived millions of years, billions of years, maybe, catastrophically then collapses within a matter of seconds, or within a matter of few minutes, and entire mass of the star, according to the general theory of relativity, is compressed into a very small volume, like a dot at the end of the sentence. It is even smaller than that, really, but that is called the space-time singularity. Covering that singularity is what is called event horizon. And very important point, as I will come to the event horizon telescope and the images and the photographs of the center of the galaxy, what is called a photon sphere. So the paradigm was that you have stellar nebula. Then if you have an average star, then that will be ultimately become red giant. This is what will happen to sun, by the way. If you want to tell your friends and your family what will happen to sun later on, even if it is 500 crores of years away, it will become a red giant, engulf the nearby planets like the Mercury and even Earth and whatever. And then finally, it will become a white dwarf. But if there are much more massive stars, then either they can become what is called a neutron star or a black hole. So the question, you see, is, do all massive stars collapse to black holes? As I said, they had made an assumption that, in order to explain the very highly energetic phenomena, we will assume, and that is the hypothesis of Roger Penrose, that all stars become black holes. But actually, does it happen that way? So scientists, you see, later on started working out more and more calculations, because in the time of Oppenheimer and Schneider, it was very difficult to really work out the general theory of relativity. But then they worked out, the calculations, and it turned out that the so-called space-time singularity, where a lot of mass is compressed, sometimes it is within black hole, and sometimes it is, outside. This is the collapse process, basically. And singularity, or the compact object forming at the center, courtesy NASA. You can see that, but since this is relevant, I'll show you the process of gravitational collapse. This just gives you an idea what a catastrophic process it is. You see, some of you might have heard the name of what is called gamma ray burst. How many have heard gamma ray burst? Many. Wonderful. So a gamma ray burst, gives out energy. How much energy? The energy that the entire sun will give during its entire lifetime. I said I have been emphasizing very long lifetime of the sun. The entire lifetime energy of the sun is given out in a gamma ray burst within a matter of few minutes. Can you imagine how much energy that would be? You see, 10 billions of years of sun radiating. So this is this catastrophic process. So gamma ray bursts are also supposed to be generated by this kind of processes. We have jets coming out of the centers of galaxies. So what I am trying to tell you is that lot of astrophysics and cosmology started being worked out based on this developments. This is a some small amount of maths. I will not emphasize on that at all at the moment. What I want to tell you right now is that Oppenheimer and Schneider had assumed that the density, for example, of the star was completely constant, center to boundary. Now, this is never really the case. In the real stars, actually, the density is higher at the center, or then it decreases slowly, tapers off as you go a little far away. So, this is, you see, a density profile where the density is slowly decreasing away from the center. I will not go into the math details, but I will just tell you that when you do all the math, then what you find is that if the density is constant throughout the star, then a black hole will happen. However, if the density is higher at the center, then actually the singularity is not fully covered and the ultra high density region becomes visible to the far away observers. The lot of work has happened, in all this connection. I will not go into the detail right now, but these are some of the, developments that have happened, on gravitational collapse, all sorts of, the physics and the astrophysics of the singularity, around the singularity is being worked out. Why? Because as I told you, singularity is singularity. It is apurva, really, unique in the real sense, in that, the densities, the temperatures, all physical quantities are so extraordinarily high near a singularity that nowhere in the universe you find any such happening anywhere. Now, if it was safely hidden within a black hole, then you had not to worry. But if it becomes visible, in fact, as I will emphasize a little later, you come face to face with, the laws of what is called quantum gravity. The string theory and, loop quantum gravity and all of that make, the theory of the universe as a whole, including all four forces. But there has not been much success despite the best of the mind working, on the, for example, string theory, loop quantum gravity, and so on. But these are all theories, you see, no observational input. But if you have a singularity visible, then the quantum gravity happenings would, actually the signals will come to you. So there might be a possibility. Robert Wald pointed out that you are face to face with, laws of quantum gravity. Once in a while, I must throw in big names, you see. But I am doing it correctly, okay? I can give you references. If you want, I can give you references. If only I tell, then you may not believe. So, the key point is the following. It is the initial data. You see, a star starts collapsing from one set of initial conditions. There are set of initial conditions. What is the density? What are the pressures? What are the different physical quantities? What is called equation of state, for example. So equation of state is something that relates pressure and the densities. If you ask questions, I'll go into detail, but right now I won't. Okay. So that is all defining what is called the set of initial conditions from which the collapse triggers. So if the initial conditions were such that the densities were completely homogeneous, as an example I am telling you, then it would be black hole. But if the density is higher at the center, which is actually more physical, then in that case the singularity becomes visible. So ये जो surface है, this is the surface where all the initial conditions are defined, and then depending on what the initial conditions are, either you have a black hole or you have a naked singularity. So as the mathematicians or statisticians know, you see, this is the space of initial data, so to say. So in that initial data space, this is the region where the singularity is visible, whereas this is the black hole. So it's a kind of Roger Penrose, the measure of data, so to say, which is black hole and which is naked singularity. The important point that I am telling you is as opposed to this, paradigm that I was showing you earlier. The massive stars going to black holes, and the featherweight low stars going to white dwarfs kind of a thing. Now you have a new paradigm, which is you see featherweight stars, the white dwarf, will take place. 8 to 10 solar mass stars will be a neutron star. But if there is a massive star, then either a black hole or exploding fireball, that is naked singularity, will develop. So I will not go into the detail, but it has been a huge, sort of debate and fight, so to say. It's the decades sort of discussion, because you see people had accepted the cosmic censor, namely only black holes will happen. Ab pura invest kar diya apne paisa. Abhi then it's going down, the stock is going down. So obviously I mean problem ho jayega na. So you see now both the black holes and exploding fireballs, but by now there are I mean not hundreds but even several hundreds of papers. I'll give one example, a paper, very interesting paper that came only yesterday, but that I'll talk about a little later. But the point is, now this paradigm is essentially theoretically accepted that when a massive star dies, either a black hole will form or a visible singularity, depending on what the initial conditions are. And then people are examining the outcomes. When Stephen Hawking accepted this, it was the first a page article in New York Times, and he concession sort of, he agreed and so on. He was in India. We had gotten him in string theory conference. He was very interested in unified theories and so on. In fact, I recall visiting when the If some of you might have seen the string theory volumes, you see Green, Schwartz and Witten. I don't know. So 3 big volumes from Cambridge University Press. So when they were published, I just happened to visit Stephen Hawking, and his office was just above the Cambridge University Press offices. So he told me that just go downstairs, buy these 3 volumes and start studying string theory. He was very excited because hopefully, string theories might create, unified theory over the years, and that has not actually happened. But anyway, on all this work, I was invited in 2009 to write an article by Scientific American. I thought it is just a popular article. I'll just write and but it was much more tough than writing a research paper. Some 10 months of very extensive correspondence with their editors. Each word you see, they are fighting about. So the meanings of the sentences and so on. So I learned a lot anyway. I say more of a lot of editors' contributions, but I mean fantastic. You realize that what kind of attention they pay to the details, and the bonus was it was a cover story. This is the German edition and the cartoon by the German editor and so on. Now the very interesting thing is the Scientific American has been at it. In 2013 they produced another special edition, collector's edition, in which they collected some 16 top research stories, in which Stephen Hawking and Avi Loeb from Harvard, all those articles are there. You can see on the net, Extreme Physics, Scientific American. So they included this my article in that one. And only even recently, 2022, they published what is called Ultimate Physics. So in that again they have reproduced, but there has been a lot of debate. In fact, this La Pava, you see, he wrote a book with a title A Naked Singularity, and Julia Keller wrote in Chicago Tribune a review of this book, where she interestingly cited my Scientific American article, What is a Naked Singularity? So it's nice, I mean, that you see how all those things go around. And recently a movie also has been made, if you just look up the net, by various sort of people. The recent developments, as I am coming to that, research papers from top academic places such as Cambridge, Perimeter, Princeton, that has been coming, a lot of discussion. You just have to look at the net. Indian work is well cited, and in fact now people have started asking for past few years that all right, they are there, fine. I mean, we are not interested in your theory. I mean, when especially I talk to the astronomers, so they say ki, theek hai, don't tell us all this mathematics. Suppose they are there, what are we going to observe out there in the skies? Tell us. And then we will try to, decide that way, because whatever is your theory, and, if it is not observationally verified, what is the use? So, you see, what are the observational signatures, which will be out there in the skies? So for past, 10, 15 years, a lot of effort has been, directed to that. There are several interesting things happening. You see, there are accretion disks around these objects, black holes and singularities. Accretion disk is a lot of matter, you see, traveling with very high velocity, because these are very strong gravitational fields. So as you go closer, as the matter falls in there, it picks up a lot of speed. And that is where this X-rays and all those things are emitted. This Chandra telescope I was telling you, and so on. So here is, you see, a singularity, for example, or a black hole, and then a lot of matter is going round, and it is heating up, and then this is called the accretion disk. and lot of very interesting phenomena is being discussed and observed. So in one collaboration with Harvard and others, we worked out in one of our papers that the accretion disk, as I was telling you, is doing a lot of emissions of X-rays and other high energy radiations. So in the black hole case, beyond a certain energy, there will not be higher frequency radiation. But in the naked singularity models, you have much higher energies. So the clear distinction is there. If you want to distinguish the two objects, then this is in our 2014 paper. There are other things also. I will not go into that, but I will emphasize what is called gravitational lensing, because gravitational lensing is something very important, and I'm just going to refer to the shadows. Now I am coming to that, the shadows of the black hole and so on. So gravitational lensing is the very important physical phenomenon which is being used actually to decipher the happening of the shadows. And but why the whole thing is important? Again, I have told, I think, basically, but the point is, if the visible singularities are occurring, then you see we are having very exciting observable implications, as I pointed out to you just before a moment. The accretion disk profiles, for example. There are several other ways, but then this is the one of the possibilities. The key point is, general relativity implies existence of strong gravity regions where both quantum gravity and general relativity come into their own. And then as Wald pointed out, and as I quoted, if censorship fails, that if the singularity is visible, then there is a literal sense we come face to face with the laws of quantum gravity. There is an explosion now, say in the skies, and this we observe. So then the question is what it is. I'll not go into this detail right now. I will come to now the Event Horizon Telescope part, because I think I would like to leave enough time for discussion. So in this final phase, I'll focus on the telescopes focusing at the center of our galaxy. This is, you see, the galactic center actually. When you see that through radio telescopes, and then the highlighted part is the actual center of the galaxy, the mysterious object that I have been talking about. And the very interesting international collaboration to be emphasized here is that they connected this Event Horizon Telescope, they connected the radio telescopes, you see, spread all over the world, many parts of the world. And connecting them, see, the bigger the telescope is, the smaller is the resolution, the smaller things you can see. If your telescope is small, then you cannot resolve much more. So this is almost Earth-sized telescope, and you need that in order to resolve the center of the the center of the galaxy, what it is. So the image that is obtained, beautifully is shown. See, one ray is coming and it is going here. At the center is a singularity or a black hole. Now you are tracing the rays, how they are behaving, what they are doing. A lot of rays, you see, coming from the background. and this is the, you see, final image that you see. Now these things happen very slowly actually. It is not as fast as you see it here. Let me play it again. Sorry. So I just press enter. Oh, I did it earlier. Enter will do it. Okay. That is always better. Go back and then come. You should see this. Perhaps you might have seen, some of you, but how the image is created. So the Event Horizon Telescope collects photon by photon, you see, the rays. So this is what typically, the kind of things that they observe, and this is the image that is actually created, you see, of the galactic center. Earlier thing was only a cartoon simulation, but this is the actual image obtained by the Event Horizon Telescope. Oxford has published my book, The Story of Collapsing Stars. You can see many of the details. Indian edition also I emphasized to them, and they have made it. So all the details. Now we have studied recently, the trajectory of stars around the galactic centers. If any of you are interested, we discuss all these topics in our course, which is going on right now actually, advanced topics, special topics, you see, in general relativity and cosmology. So we discuss those topics, in fact, over there. But we study, you see, the stars go, you see, round the galactic center actually. They are, one of them is S2 stars. So you see, some of our students, you see, Parth Babania and Ashok Joshi and many others now here also, Kaushiki Jai, and we are thinking about all these issues. But this is the kind of trajectories, and one very interesting phenomena that we observed is we observed a retrograde is a precession effect while going around a singularity as opposed to going around a black hole. You have heard perihelion of Mercury. What happens is, you see, the Mercury goes around the sun, but it is not the same orbit all the time. You see, it is going like this, but then bends a little, then bends a little, bends a little. So it's a perihelion shift, what it is called. But when we took naked singularity and studied the trajectories around that, then it was happening other way around in a different sense. So you see, all these things are creating a lot of interest. Ki ye sab kya ho raha hai? What all things are happening, you see. And now I told you about the images. I'll tell you more if you ask any questions, but the now really final part, I said final part, but now this gravitational waves, you see the LIGO and the collision of two black holes. You might have seen this image also. The point is that, I hope you can see this. See, a star is orbiting around the galactic center, and it is making certain specific orbits. Now, how do you know the main question, as I have been emphasizing, is that what the hell is the nature of this mysterious object? In the you see recent Event Horizon Telescope papers which they published, so they cited our work in detail, because you see the black hole model is not fully explaining the current image. There are issues of the bending and the angular resolution and various things. So they used our models also. Suppose the event horizon is not there, then what? So it's a debate, it's a discussion. But they said that the singularity, JMN singularity, that I had displayed, this accretion disk wala jo jo model that I was saying. So they say it could be the best black hole mimicker. That is, if it is not a black hole, then it could be this naked singularity object over there. The point is that what is, you photograph to le liya, you see, but still a photograph to le liya, you see, it might be a picture from, I don't know, I mean from some street camera or some happening kahin pe hua hoga. तो बैठ के पूरी टीम को decipher, they have to decipher actually what might have happened. So the actual nature of the object is a mystery. Black hole model was very successful earlier, or at least it was assumed, and then data was fitted to that. But you see, now there are problems with that, and that is why like Kip Thorne here, in the images, the Kip Thorne is the sort of kind of a important architect of gravitational waves detection and so on. So in his lecture, he was saying that the stars are going around this object, say central body, and then he asked this question. This talk is available on the YouTube if you want to. We have just taken slides from there. So then he asked this question, that what if the central object is not a black hole? And then he said, for example, a naked singularity, that is the singularity not hidden in the and then he said that then the trajectories would be very different. That is, they will be very chaotic. And this is what we are right now examining. See what kind of stellar motion will be there around these objects and so on. This is the Bulgarian Academy of Sciences paper that just came yesterday. In fact, you can see the date actually, 2303. So maybe it is not 26 March. Yeah. So okay, not yesterday, but day before. Polarized image of equatorial emission in the horizonless spacetimes, naked singularities. So this group is there from the Bulgarian Academy of Sciences. So they cite and quote the Event Horizon Telescope papers in detail, actually. And then they use, the naked singularity models, or the horizonless objects, or the exotic compact objects, as they call it. So then they do, a lot of studies where the problems are happening, in modeling the image, in trying to understand the object. There have been, many collaborators, students who have been, working with a lot of attention, and we are, here also working on all those things. So we have a good group here, and we are trying to build up various discussions. We have just begun, and it is the energy of all this, you see, people and their interest that kind of, I should say, sustains me also into, going into more and more of these exciting issues and questions. So thank you very much for your patience.
Namaste, sir. Tanmay Vyas.
Nice to see you. Thank you.
Just wanted to know one thing, that the naked eye singularity that we are talking about, can we replace the SMBH in our own galaxy center as a naked eye singularity, or it is SMBH?
In fact, I did not, you see, display here their discussion from their papers. In fact, I have their citations. So they have, in fact, given a detailed discussion as to under what situations it could be actually a naked singularity, rather than being, actually, naked singularity also, I would say it's a black hole without horizon.
So the photographs or whatever the animation that I think one lady is collecting since 1994 about the center of our galaxy, there we have never seen the event horizon or anything. Whenever it has been shown in there is a kind of a trajectory of different stars that are going in a random motion, and from that only I believe that the mass of that particular naked eye singularity or whatever SMBH is being judged. Is it?
Yeah, you are absolutely right. You see, what we have actually done is photograph liya hai. Sir, who is this person, or what is this object, or what is its nature, and so on, it is still far, far, far from clear. And in M87, it was still better because it was a galaxy out there, and very massive galaxy also, bigger, center. But for our galactic center, it is very difficult because the number one, the object is much smaller, 1,000 times, you see, less, of the order less mass. And then when you are watching, within your own galaxy, so then there is a lot of, intervening matter and all that. So what we have concretely achieved is, you see, this Nobel Prize was given to Roger Penrose, Guess, and who is the third person? Andrea, and the third person, Genzel, I think. Genzel, I forget the first name. Now, the Roger Penrose Nobel Prize was, you see, for the discovery or for his theorem. It's very interesting that a theorem has been given, Nobel Prize. But what they, sort of said there is that general relativity predicts that a space-time singularity occurs. This is what his theorem is, and for that he got the Nobel Prize. The other two people showed that there is a lot of mass. This much of mass is concentrated over there. So my friend Ramesh Narayan calls it, an astrophysical black hole. So astrophysical black hole means a lot of mass in a small region. It doesn't have to have, this mathematical event horizon and all that. So when a lot of mass is concentrated in a small enough region, it is a black hole. But so what we know, what we read is, you see, a lot of mass is focused over there. But whether event horizon is there or not, and now if it is not there, then there are many interesting observational consequences. So this event horizon papers do discuss in great detail the possibility of a naked singularity, and they also cite our papers.
Good evening, sir. So my name is Adyan, and I actually had a question that how does the accretion disk emit X-rays and other rays that you said? So what is the process behind it?
Yeah, it's a very interesting point. In fact, again, a huge amount of work is being done in numerical simulations and modeling. See, what happens is the following. You have, as I was just mentioning, a very, high density as well as very high mass object. Like I was showing the, center, the bulge of the galaxy, or even stars can also work that way. Now, you have this object, then what happens is there is a lot of matter, you see, in the surroundings. And all this matter is being attracted by this very compact object. And that entire matter is, you see, circling, swirling, and, going towards the center. As it goes closer and closer, it becomes, higher and higher velocity of the particles. The particles which are, they can be electrons, they can be protons, they could be charged particles, whatever. Now, when they go very, very fast, even approaching the velocity of light, so that creates, you see, a lot of heat also. Lot of heat and lot of radiation is created. You know that any moving charge is creating also radiation. So that now modeling of that accretion disk actually is the thing. Whether it is a thin disk, whether it is a thick disk, a lot of work is going on. So this is the very fast motion of the particles is creating this radiations.
Like you mentioned that if stars are rotating, like moving around a singularity, then the dynamics of motion becomes more chaotic. Like, so why does it become more chaotic?
Well, right now, all I can say is we actually study the mathematical models. We have, you see, this strong curvature region. We let the stars, you see, move. We have to use the Einstein theory. We have to take the metric, what is called metric, which is, you see, depicting the gravitational potentials. And then we just study what is dictated by the general theory of relativity equations. And it turns out that the motions are different. The physical reason, I think you and me can, debate more, because this is very frontier thing actually. And what is the physical reason? Well, that is the dynamics of gravity actually. That is doing it. So it is, you see, the property of very strong gravitational fields, if I try to be little more precise. And a lot of, very strange things happen in very strong gravity fields. Black hole is one example. Time warps or the wormholes, you see, I didn't even touch, many very interesting topics. Maybe in future, if Sarthak wants, I'll tell about wormholes. Thank you. But the point is that there are, many, many interesting phenomena which are, being debated very sort of intensely at the moment. But it is all the dynamics of, Einstein equations, so to say.
Thank
you. Okay.
Hello, sir. I'm Yash from PhD in Physics at Ahmedabad University. I had a question about telescopes are observing far away in the universe. So the type of data, the different physical quantities. So I had a question: which physical quantities are we get as a data? And then the second question is, to generate the image of black hole, what type of process is done on the data to generate the image of black hole? You can just brief it.
That's a very detailed and intensive numerical, simulation. He was just referring to, some lady, I forget her name, at MIT. You see, so it's a very huge data, and someone was saying that if you put the CDs on the top of each other, from here it will reach moon or some such thing. So it's a very big data, and I am not an expert. I must confess to, do the sort of But what is done is, you see, you focus over there. For example, this particular image you see of M87 center or the our own galactic center image, that also is done, over a long period of time. It doesn't, आपने photo ले लिया बाहर यहाँ, so it doesn't happen like that. So it is collected photon by photon, then how the data is merged, and teams work on that to create and to put everything into perspective. But there are lots of checks and rechecks so that you get an authentic image.
So I'll just read out the question that we have here. We have 3 questions from the online audience. Harshvardhan Singh is asking if you can give a detailed information on TON 618 black hole. That's a very specific question, I think.
Read it again. Which black hole?
TON 618 black hole.
I see. This I will have to look up, but all black holes have basically, the feature that they have event horizon and they have accretion disk. Now, I do not know the mass of this black hole actually, how massive it is. If you know Harshvardhan, right?
Yeah, Harshvardhan.
If you know the mass, then I can tell you little more because black hole is characterized basically by its mass. Okay.
Yeah.
There are 3 parameters actually: mass, charge, and angular momentum. But charge is sort of out of question because people think that they won't have any significant charge. So rotation also is believed to be generally small. So mass is what dictates the properties. So, but in the meantime, we can take other questions.
Right.
The point, okay, just I'll add one comment that if the mass is large, then the accretion disk will be very powerful. And the X-ray emission will be very powerful. That much I can say. Okay.
So we have another question from a student from, I think, Ahmedabad University. He's asking that how do we determine the age?
यहाँ नहीं है.
No.
Online में है.
I can say from the name. But how do we determine the age of stars? How long a star lives and when it dies? So
How long? Sorry.
how do we determine the age of stars?
Yeah.
How long a star lives and when it dies?
I think, partly I alluded to that.
Yes.
It is really the mass of the star. Total mass of how heavy is the star, that determines its age. Like, for example, for sun, I said that, given its mass, it will live so much, and that is determined by the nuclear processes within the star. If they are very heavy, then a few million
Right.
of
And then
years.
also, I think in great detail you explain what happens when they die, right?
That's right. That is the gravitational collapse process.
So then we have a question from Sonal, who's asking, as mentioned by Kip Thorne regarding chaotic trajectories of particles around NS, I think that is nebula star. If we can observe
Naked singularity.
naked singularity, sorry. If we can observe such trajectories. So I don't understand where the question is. Probably I'll.
Yeah.
Can you?
Yeah, I understand. So can we? So yes, see, that is actually the big effort going on. There is a mission called Gravity, and another mission called Symphony. So they are actually trying to observe the trajectories around the the center of the galaxy of this S2 star and other stars. So this prediction chaotic behavior would come out of these observations if that is there. So you see what kind of motion is there. This missions will tell us, and they are also fitting it with various metrics in the Einstein theory. So these missions are going on, and actually one of the pictures I showed of the trajectories, that was around the center of the galaxy.
Before we move on, I think this is very, easy and important question, but I think important question. Can you, from Viral, I was asking, can you suggest any best source where he can or she, anybody, can get more information about this topic? So I think this is something probably.
There is a wonderful book by Kip Thorne. You see, it is little old, Black Holes and Time Warps. The a thick book of some 400 pages, and he gives the history also of the entire topic and so on. A smaller 200-page book is that of mine. I showed, you see, the story of collapsing stars, the Oxford publication. So there also I describe quite some details of these issues.
So the good idea would be to read the books and not just depend on YouTube videos, right?
Oh, definitely, no question about that. When you read a story, written by Kip Thorne, for example, as to when he met John Wheeler and what they talked, and तो ये वीडियो में कैसे आ सकता है? So videos are good, you see, for one purpose, and the books are good for another purpose, and we have both today. So very lucky. But as you very correctly, clearly, since I see so many students also over here, so you have to go to the books also, because I have seen things. We make reports, you see, in the university, and we ask them to prepare the research projects and so on. So most of the references are videos. Sometimes, not for everybody. तो मुझे बाहर जाके फिर ये लोग so not for everyone, but sometimes I see such things. So you see, you have to go to such books. So it's a very good question. Thank you.
Any questions from? Yes.
Hello. Hello. Yeah, I'm Shaurya. I work at the Global Center for Environment and Energy. I have a question that is connected to sustainability and cosmology. The question is like, for example, the projects like Large Hadron Collider or LIGO, they use a lot of resources. So is the community looking at the issue of sustainability within this kind of projects? And at a broader level, what's your thought about how do you connect cosmology and the idea of sustainability? What's the intersection that you as a
Cosmology and
sustainability as a field?
yeah.
At a broader level, what's your intersection point of view?
A very interesting question. I think I'll try to tell it in my own way. Cosmology, I think, makes you realize, you see, your true place in the universe. Now, many questions actually come up because you see, we don't realize our true place in the universe. And we think sometimes, you see, that we are sorry, this is personal opinion. So you may or may not agree, but sometimes we think we are too important. More important than and we are all important, no question about that. But so that if you have that degree of politeness or your place in the framework of cosmos, then you will see yourself as part of the universe. Then that already brings in a little bit of harmony, so to say. In my view, if you maintain this frame of mind, that I am a part of the universe, part of the cosmos, then I think slowly that will lead to use of resources and so on, or rather derive the joy from cosmic explorations, I would say, rather than use of resources. And if you if you use the resources in smaller magnitude, then your joy will become finer. So this is one thing, but on a more practical level, space is also telling us much more about environment. For example, I only the other day I heard that all this global warming and all this is कुछ नहीं है इसमें, you see, it is all bogus. Yes, Only recently I heard. I used to hear this 10 years ago or, earlier. But this was a meeting of, some industry people, and they did say that. कि ऐसा कुछ है नहीं. Now you see, the space is, getting a much more accurate data compared to, what was available earlier. You must have, heard about this Elon Musk and, his satellite, constellations being placed, smaller satellites and so on. So I think this data will, bring out the climate change on a much stronger scientific, footing, so that, the evidence becomes much, much more stronger. All in all, I think I would say that, yeah, the cosmic way of thinking, that is the biggest contribution the cosmology would have. But then there are also other practical things like, if you understand the secrets of gravity or secrets of the star better, then you will know the secret of the fusion energy. You will not know about the fusion unless you examine gravity in much more detail. That much I can say. Now, if the fusion energy is used, for example, then it would be much, much cleaner energy. Right now, we are, trying with this various forms of clean energy, but still we know that how much coal dependence is there. But fusion energy, if we realize, even atomic reactors have a lot of problems. I mean, we have been seeing the debates. Some people say that it is much cleaner. Some people say there are dangers. But the fusion energy. So I would say that all these things, see, the main thing is energy question. This entire sustainability is related with, our energy requirements. So the cleaner the source of the energy, but I am not, the true expert. Since you give me the opportunity, so I expressed a few thoughts. I am not sure, but we can discuss more on this separately. Yeah.
Good evening, sir. Sir, I wanted to ask a question that in case of naked singularity, we don't have event horizon. Then is there any other kind of a boundary that we consider?
Sometimes we consider boundary conditions, you see, that is in mathematical sense. But as such, the causal communication, is there from very close to the singularity. What do I mean by causal communication? The rays can come from very close to the singularity, but if there is event horizon, only outside the event horizon the rays can come. So other than that, there is no other boundary.
If we don't have clear boundary, then how do we assign entropy to naked singularity?
That is another, important frontier question. We do talk of, the processes close to the singularity, like Big Bang, for example. Big Bang is a naked singularity, actually, because the rays can come from Big Bang to us. We are connected to Big Bang and it is a naked singularity. So similarly, here now, this will be mini Big Bangs, so to say. It was there in one of my slides, actually. If I can go back, let us see. This is connected, or can I? Yeah. In fact, I didn't, spend time on that. And now I'll go back and I'll locate the correct slide. So this is the slide. I think it is written, naked singularity is like a mini Big Bang. So you are connected, with the emissions from very close to the singularity. Big Bang, in a big way, the entire universe is created from there. But here a star is collapsing, creating a singularity. And it's like, from very close to the, singularity, you are getting the emissions. Was that your question? Did I answer it? Entropy, so we have to study the physical processes just as we do early universe studies, for example, today. So that we have to do. Many things are happening actually. It's a frontier research topic.
Hello.
Ah.
Good evening, sir. Good evening, sir. Sir, you just said, is it what? Okay. You just said that mass is one of the criteria. So, in this naked singularity, is there any mathematical model or anything where there has been known that this much is the mass, limit of mass after which you can create one?
Yeah, in this cases, you see, as I showed you in this figure, it is the initial conditions that really decide the outcome of the gravitational collapse one way or the other. Initial conditions in terms of the density and pressures, for example, whether the density is inhomogeneous, higher at the center, what is the equation of state. So in addition to the mass, it is the initial data which is deciding the final state.
Initial as in when the star is taking birth or?
When it starts collapsing, when it is dying, rather than taking birth.
One more question. So in general theory of relativity lectures, you said that when the gravitational collapse is happening, at that time when the singularity is happening, at that time event horizon is also just forming. So that is one phase when there is naked singularity, right? So is it that time only when you can study, or is it possible, just a thought, that after event horizon has formed, there can be a possibility that it gets away because of, let's say, Hawking radiation, maybe. So it gets away and then you may get a naked singularity. So
Yes,
is it
good point, good point.
scientifically possible?
Yeah. In the class we discussed one model, one particular model, but many models have been studied where event horizon does not form, for example, at all. Like these models that I mentioned of JM and Joshi Malafarina Narayan models. So there the event horizon doesn't come. But if it has formed, then the singularity is hidden. So then it's a momentary event like singularity that is visible. So all this discussion and studies are going on. But the important point is, you see the very intriguing different signatures that we are getting in both the cases of this astrophysical phenomena.
Thank you so much, sir.
Namaste, sir. My name is Bharak, and my question is based on mathematical model. Like, can we describe singularity as a Dirac delta function or as emerging infinity in the solving the Lagrange of the system, as what we are describing in the QFT, specifically IR or the UV radiation, UV infinities?
It's very intriguing question. In fact, there was a very big debate on what is a singularity, how to characterize it actually. So Robert Garrosh of USA Chicago University, and you see Hawking himself and Penrose, they have contributed in a big way in characterizing what, which way, what to call a space-time singularity actually. And you see, it's all little mathematical, geodesic incompleteness of the trajectories, and then how the curvatures grow in the limit of approach to the singularity and all that. But does this answer your question?
Actually, my question. My question is actually how do we interpret the singularity in terms of mathematical models like delta function?
Yeah.
What
So,
we are
yeah. So one thing that happens is, you see, the physical quantities will blow up there. The space-time curvatures will blow in the vicinity of the singularity. For example, if you take an object, then it is characterized mathematically by means of what are called Jacobi vector fields.
Jacobi matrix.
Jacobi vector fields, they define a volume element. So as you approach the singularity, this volume element shrinks to zero size. So that is interpreted as saying that all physical objects are destroyed to zero vanishing size. So this things can be mathematically worked out and characterized. So some of our colleagues and students have done these things. So we can give you more details on this if you are interested.